All right, the focus of this lesson is going to be completing the square. And in order to even want to complete the square, you'd have to understand any sort of motivation to do that. So we wanted to show you some simpler problems leading up to it, which are places where square roots come in pretty handy. And you guys have seen a little bit of this when we've worked with a vertex form and solved for the x-intercepts. Notice in example 11, the entire square here, 3x squared, x is only contained as part of that square, which means it'd be a good place to use square roots. So I'm going to subtract 5 from both sides, then divide by 3, and I'm going to square root both sides. So if I want to use square roots, oops, sorry about that. So if I want to solve by using square roots, I need to have that perfect square. So when we initially look at example 12, it doesn't feel like the same situation because this x is squared, but this one isn't. So square roots wouldn't be a good thing here unless you could write all of these x's as part of one perfect square, which if you factor this, so go off to the side, use your method, guess and check, the diamond with the grouping, bottoms up, whatever it is that you guys use to factor. And notice that this factors as x plus 6 times x plus 6, or x plus 6 squared. So when we square root this, we actually can now because all of the x's could be gathered up into one perfect square. And this would give us x plus 6 equals plus or minus 3. We'd want to subtract 6, and there are two solutions here. The positive 3 minus 6, which is negative 3, and the negative 3 minus 6, which is negative 9. So again, this worked so nicely because when I factored it, I normally don't want to factor things set equal to 9, but this only worked because it was a perfect square. So the idea behind completing the square is to take things that are not perfect squares, that don't fit this model, and make them perfect squares so that you can use this model. So what makes something a perfect square? So notice a pattern. I'm going to go off to the side over here. If we multiply together things that are perfect squares, so two of the same things, at the beginning you get a perfect square because these two exact same things multiply each other and make that squared. At the end, you get a perfect square because these two numbers are exactly the same and multiply to make a perfect square. Well, what do you get in the middle? Well, if the first numbers are the same and the second numbers are the same, then when the first number from this first factor multiplies the second one over here, you get their product. The second one over here times the first one over here ends up producing the same product. So you get two of the exact same things here, which we would normally write as 6x, but I want to emphasize that it's two of the same things. So if we wanted to work backwards, like in part A, we're basically thinking about how 18 is really two 9s being added together if it's perfect squares. And if it was two 9s being added together, it must have been something that looked like this, so that you got those x squared at the beginning, and then you got a 9x here and a 9x here. So the ending term is going to be 9 times 9, which is 81. So we want to kind of procedurize this so that we don't have to keep walking through that every time as the numbers get more difficult. So notice what we did is the first thing we did is we took 18 and we split it in half. So to complete the square, and to complete it means just to find that constant at the end, we're taking the coefficient of the middle term, the b, we're dividing it by 2. So 18 got split in half and became 9. And then remember, it was two 9s multiplied together that made 81. So it was this value, this 9 squared, that made that 81. Okay, and in this one, C was 81. So now we can use that idea instead of having to walk through the whole thing ourselves. So in part B, the B value is 9. Negative 9 divided by 2. And I know a lot of you guys are tempted to write decimals, but this is actually a lot easier to simplify if we're not using calculators in a fractional form than a decimal form. So that's what you're going to see us do here. So this becomes 81 over 4. So the number that I want to add right here, I know it looks a little strange, but is 81 over 4. 9 was an odd number, so it was a little more difficult. Now in part C, 2 is not a perfect square. So what we'd want to do is we actually want to remove the 2 so that we can complete the square without it there, and then kind of look at what should be there. So we already did this work. If -9 is the middle term's coefficient, we figured out that 81/4 in the last example is what you'd add on to complete the square. 81/4 is not C. It is C with 2 factored out of it. So now we want to think, what were all these numbers if 2 was multiplied back into them? It'd be 2r squared minus 18r, which we already knew was the case. And then what's that last value, which would be C? You have 81/4 being multiplied by 2. And so that would give us 81/2. So that is what we get there. So now what we're going to try and do is we're going to make you solve problems this way. Now on your exam, we're not going to make you solve one specific way, but what we want is that you guys have had practice with all the different ways so that you can actually decide which ones you want to use when, instead of just using only one that you know out of necessity when it could be really inconvenient at different times. So when I look at part A, right now we are making you complete the square. So we will in the homework, so that you get practice and you can make decisions about when and how and if you would use this. But then on the exam, we won't make you work it out this specific way. So if I want to complete the square, 16 is a perfect square, but not the perfect square for this polynomial because that wouldn't work with 2. So what I want to do is I want to kind of remove 16. It's not the number I want for the perfect square, so I would add it to both sides. And then I would leave it open so that I could add the constant that I wanted, which seems a little odd because normally we wouldn't think that we can just add whatever we want to some expression, and normally we can't. But this is an equation, 2 equal counterparts, so we can use that addition property of equality in order to be able to add something to both sides of this. So it only works in this case where we can use that property of equality. So to complete the square, my kind of shortcut here, or my formula, was to take that middle coefficient, divide it by 2 and square it. And in this case, that works out to be 1. So the number I'd want to add is 1. If I've added 1 to the left side, I would also need to add 1 to the right side. Okay? So after doing that, I get 17 on the right side. And then think about what you are doing. So this is a big difference between Algebra 2 and Algebra 1. We don't just want a procedural kind of robotic thing. We want to understand what we were trying to do here. If you were trying to complete the square, you were trying to make a perfect square. So it should make sense that every time after you've completed the square, that your next step would be to write that polynomial in its factored form as a perfect square. So if I did this correctly, that should factor, and you can go off to the side and factor. Or if you're confident in your perfect square, you can just think about what squared would make the beginning and what squared would make the end. And then you know that if you wrote it out and FOILed it, you would get this middle term in between. Now we have everything set up in that perfect square manner, so we can square root both sides and use radicals as a way for solving. So we would get x plus 1 on the left side and positive or negative square root of 17 on the right. We're going to subtract 1 from each of these, and we're going to get 2 x values that would solve this quadratic, -1 plus rad 17 or -1 minus rad 17. We're going to do the same thing again in part B. Okay. The difference here is that, first of all, 12 is not a perfect square, so I know it's not the number that I want to use most likely. So I can move that over to the other side. And I also have a big issue here. I have this lead coefficient. We can't complete the square with the lead coefficient because we didn't explore what happens when there's other numbers there in front. So what we're going to have to do is divide everything by 2. And again, this is okay because we have 2 sides of an equation. We can divide both sides by 2. So I get x squared minus 7/2x equals -6. And now my focus is what constant should I add to the left side to make it a perfect square? And don't be frustrated by the fact you have a fraction. It's not super convenient, but you guys are capable of doing this. You just have to walk through the same things. So remember, to complete the square, we take that b coefficient, which in this case is already a fraction. We want to divide it by 2, and then we want to square it. And I want you to really not be concerned about this whole fraction within a fraction thing here. What I want you to do is think about how you would have done this a long time ago. If someone gave you negative 7 over 2 divided by 2, that's negative 7 over 2 times 1/2, which is negative 7 over 4. And you're supposed to square that. So that's going to give you 49 over 16. So the perfect square number that I want to add here is 49 over 16. And again, I need to add an equivalent amount to the other side of the equation. Having these two sides is really, again, the only reason I can add in what I want. So I need to make sure I'm using that equality, that they're both getting that amount. And so again, with my factoring patterns or techniques, I should be able to tell that the left side is going to factor as x. With the second term of 7 over 4, I'm getting that from the square root of this 49 over 16. And then if I FOIL it out, I see it does make 7 over 2 in the middle, and I specifically want it to make a negative term, so I would make sure that they are negative. On the right side, I want to add these two things together, but I need a common denominator. So I'm going to make a common denominator of 16 by multiplying top and bottom of this first value by 16. And so I get a 16 as a denominator, and in my numerator, I have negative 96 plus 49, which is negative 47. And now I would want to square root both sides to get rid of the radical. And actually on this one, you can stop here. I just square rooted a negative, which you guys know to mean that there's no solution because we don't have a real number for that. In this unit, we're going to explore how to write solutions when they aren't real solutions, but still fit into the world of mathematics in some way. But we're not there yet. So for this one, we could just write no solution. Okay. All right, the last example that we're going to look at is example 15, where we are going to focus on rewriting the equations in vertex form. So remember, our vertex form looks like this. Notice the perfect square. And that should be familiar to you because we had to use square roots when solving those for our x-intercepts. So here we're not actually solving. We're not going to get an x equals, but we do want to take everything that contains x and somehow fit it into a perfect square. So when you look at something like part A, and you're trying to do this, basically these two terms have x, and this third term, this constant, isn't a perfect square, so I know it's not going to be part of this perfect square. And that's okay because there's a spot for it out here. So what I'm thinking in my head is I've kind of split it into two groups. The group that's going to be part of the perfect square, and then the group that's not. And these parentheses kind of help me distinguish that. For the group that is part of the perfect square, remember what we do to complete the square. We take that b coefficient, divide it by 2, and square it, which in this case is 25. But if we add 25 to the right side of the equation, we would also add 25 to the left side of the equation. And because we're writing an equation, we really don't want anything over there with y. We kind of want the y alone. So we can actually move the 25 back over to the right side of the equation. And some of you will catch on to this to mean that you could have just, as I rewrite this, you'll kind of see, since you added 25 to one side, you could also subtract 25 from the same side, and it's like you've added nothing, but you've written it in a way that we prefer at this moment. Now that should make this factor as a perfect square, and in this case that factors as x plus 5 squared, and then 27 minus 25 is 2, so I get my 2. So my a value is a 1, My h is a -5 and my k is a 2. And then I could go on if I was directed or needed to finding the x-intercepts with square roots here or graphing it from its vertex form. So again, we're going to look at the same thing for part B. And again, the issue with part B is this lead coefficient of 2. And this time I don't really want to divide both sides by 2 because then over here I'm going to have like a y over 2, which is kind of weird. So instead, I'm first kind of grouping in my mind these things I'm going to try to make the perfect square out of, and this I'm not. Okay. So, but I can't have the 2 in here. So I factor that 2 out of that set of parentheses. That makes that middle term 7 over 2x. And the 10 doesn't get a 2 factored out of it. It's not part of that group. So you can see right now, if you did distribute back the 2, we'd have exactly what we had to begin with. And now we want to complete the square. So to get what we're going to add, remember what we do here. We take this middle coefficient, we divide it by 2, and then we square it. And remember what we said that means, that we're actually going to take 7 over 2 and divide it by 2, which is like 7 over 2 times 1/2, which is 7 over 4. And when I square that, I'd get 49 over 16. Now you need to be really careful here about the amount that you just got. You wrote down the number 49 over 16, but what you wrote is not actually worth 49 over 16. And let me show you why. That 49 over 16 is a portion of a quantity that's enclosed by parentheses and being multiplied by 2. So the 49 over 16 is not worth 49 over 16. It's worth 49 over 16 multiplied by 2. Okay, so let's think about what that is. If I take 49 over 16 and I times it by 2, I get 49 over 8. So this is really worth 49 over 8. So to even that out, I will add 49 over 8 to the other side. Or if you caught on to what we were doing before without doing the extra step, but doing the extra step is fine. We have 2x squared plus 7 over 2x plus 49 over 16 plus 10, and then we should have minus 49 over 8. And then we're going to keep rewriting this so we can get that perfect vertex form. So here I have an a value of 2. Based on the numbers here, this is going to factor as x plus 7 over 4 squared. And then for that k value, I'm going to give 10 a common denominator of 8. So I'm going to, when I do that, I get a denominator of 8, a numerator of 31. And so this is my equation with an a value of 2, an h value of negative 7 over 4, and a k value of 31 over 8. They're not nice numbers, but you could still plot them and graph them from that vertex form.